Okay, so the recording is started. For those who didn't get a chance to join us for the live lecture today, I just played a video. It's got copyrighted music, so I'm not putting it as a part of the recorded session, but you can watch it on your own under vector fields, section 16.1, far, far away. You can have a look at the video. It's just a bit of a teaser as to what we are doing now in the course. So the idea with where we're getting to now in the course is we are now looking at functions that take multiple inputs, which is nothing unusual. We've been looking at functions this entire semester, which take multiple inputs. So x, y values or x, y, z values, or even higher dimensions. But now we're looking at their outputs as also taking on multiple values as well. So these are functions that have multiple inputs, or we can think of them as vector inputs, and then they have vector outputs. So just a couple of examples of where we would see such things. So here's a graph of this is a weather pattern across the world, and the vectors are color coded, and that's just to indicate magnitude. And there's a scale down at the bottom that indicates the magnitude of the vectors. But these are, vectors, for example, that represent fluid flow. So current flow in the ocean, for example. What else could we do? We could look at, for example, a magnet, and look at the electric force field generated by a magnet. And again, that's just a magnetic force that's being applied at any given point around the magnetic poles, and the length of the arrow indicates the direction of the force and the magnitude of the force. Here's an example where we've actually got a formula that's giving the vector field. And so there's F. Now, because capital F is outputting a vector, we're going to use a vector symbol on top of it. So it's capital F with an arrow on top of it. F of x, y. So this means at any point in the xy plane, we're going to assign a vector to that point. And the vector that we assign is given by, well, its I component is given by negative y over the distance from the point to the origin. And its y component, or its j hat component, is given by x over the distance that the point is to the origin. And when we draw a vector field, we don't draw all of the vectors, because that would be attaching a vector to every single point in the plane. And that would just be, there'd be infinite many points, and we'd have to attach vectors to all of them. It would just become a confusing mess. The point is though that there is a vector associated at every point, but we just draw enough of them to get a feel for what's going on. And so there's a few of these vectors drawn at various points. So at point 1, 0, you can see the vectors pointing straight up. At the point 0, 3, the vectors pointing to the left, and so on. And these vectors seem to be spiraling around in some sort of circular direction. So that's another example of a vector field. We can also do the same thing in space as well. So if E is a region in space, in R3, we can assign a vector field on E, well, on all of R3, but it could be specified just to the region E. And it just assigns to each point in space a three-dimensional vector. So there's some examples of vector fields in space. And again, you can think of these as gravitational force fields. So any point in space is going to be acted upon by some gravitational force. And the vector points in the direction that the force is being applied at that point. We can think of these as magnetic fields. You can think of these as fluids. So this is a body of water, a region of water, and these vectors are pointing in the direction that the fluid is moving in, and the length is the speed. So these would be velocity vectors for the fluid. So there's various different interpretations we can have of these. They'd all depend on the particular example you're interested in. So let's go ahead and look at actually constructing a vector field. So in this example, we're going to assume that we've got an object with mass capital M, and it's located at the origin. Think of this as like a planet, like Earth. So we've got Earth at the origin, a big mass, mass capital M. And let an object P with mass little m be located at the point x, y, z. And what we're going to do is we're going to show that the gravitational force acting on that object at point P by the mass at the origin is given by this, and it's might be difficult to see in there, but you got to look closely, given by this vector field. So this is F with a vector hat on top. So this is a vector field at the point P is given by, there's a few constants thrown in there, and little m, big G, and then we've got x with an arrow on top. So that's a vector x. So this is the point P goes in, and what comes out is a vector scaled up in that way. So let's see why this is the case. So what we have is we've got a big mass, capital M, at the origin. We've got a little mass, little m, at a point P. And we want to figure out what is the force vector that is acting on this mass little m by this big mass, capital M. And so that's going to be a force that acts in this direction. It's going to be an attractive force, a gravitational force. And we need to figure out what that is. So the first thing to note is from physics, we have what is known as the inverse square law. And the inverse square law is telling us how the magnetic, or in this case, the gravitational force is related to the two masses themselves and the distance between them. So what we have is the magnitude, I'll label this capital F with an arrow on top. So we're looking for that force. So the magnitude of it is equal to little m, big M, this gravitational constant, capital G, over the distance between the two masses squared. So it's little m, big G over the square of the distance between them. That's the inverse square law. And this is what's also referred to as, maybe I should write the word. It's the universal gravitation law. Universal gravitation law. So this is the law we use for the gravitational forces between two masses. In the case that the mass m is the Earth and our other mass, little m, is near the surface of the Earth, then we use m little g, and little g is just some combination of the mass of the Earth, the big G gravitational constant, and the radius of the Earth, all thrown together to give that. So this will reduce to the force that we get, the gravitational force acting on an object at Earth's surface, but this is the universal gravitation law. This is between any two masses. This is how the gravitational forces behave. So we've got our inverse square law, which means we know the magnitude of F. We know the magnitude of this force. We also need to know what the direction is that this force is acting. So the direction of force, well, that is going to be given by the position vector, and then we will scale it by its length. So that's the direction the force is acting in. That's that direction. Actually, there's one more thing I have to add to it. I got to add a negative sign there, because the direction the force is acting is towards the origin, from that point P towards the origin. So we can put these two things together to get the force vector. And so the force vector at that point P is given by the magnitude over square the distance between them. That's a scalar, times the direction vector. And so that we can simplify as negative little m, big M, G over magnitude cubed of the position vector times the position vector. And so there is our gravitational force acting on a mass little m at a point P, given that we've got a large mass big M at the origin. So what we've just done here is we've constructed a vector field. This is a vector field. At any given point in space, we've attached a vector to it, which is the gravitational force acting on the mass at that point in space. Okay, so let's have a look at another vector field that we're already familiar with. This is the gradient vector field. So if f is a scalar function of 3 variables, so the kind of function we've been dealing with most of the course, we could take its gradient. So this is a vector that we've constructed from a scalar function. It's the vector of derivatives. So in this case, if f is a scalar function of 3 variables, x, y, z, then its gradient is going to have 3 components: the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z. And putting those 3 partial derivatives as the components of this vector, we get a vector field. And this is known as the gradient vector field. So this is one that we've been familiar with already. So it turns out that we've actually been using vector fields a little bit already. And so here's an example. Let's find the gradient vector field of this scalar function. So what we're going to do is we are going to take its partial derivatives and throw them together as the components of this gradient function. So we're going to have to construct these partial derivatives, and these, by symmetry, these partial derivatives are all really going to be of the same flavor. That's just the variables changed. So the first one we get, which is, maybe we'll write it out in full. So I will think of this as x squared plus y squared plus z squared to the negative 1/2. So when we differentiate it, we get the negative half coming down, and then we multiply by the derivative of the inside function, which is 2 times whatever variable we're at. So the 2 and the half would cancel and just leave us with a negative of the variable we're differentiating with respect to. And then what's downstairs is going to be x squared plus y squared plus z squared to the 3/2 now. So when I differentiate at power of negative 1/2, I get negative 3/2 in the exponent. So that means it's downstairs as a power of 3/2. Similarly for the next one, it's negative y, x squared plus y squared plus z squared to the 3/2. And we get negative z times x squared plus y squared plus z squared to the 3/2. And so there's our gradient vector field. We can simplify this a little bit in how we write it. So we could write it as negative, it's really the vector x of components x, y, and z, but they've all been scaled. And they've been scaled by the length of x cubed, because the length of x is that square root in the denominator, and then that square root is being cubed. So this is just a simplified way to write that corresponding gradient vector field. Now, if you've got a keen eye and you're looking at this, you're thinking to yourself, wait a minute, that is the same vector field that cropped up top here. It's just this force vector field, capital F, is that negative x over the magnitude of x cubed with some extra constants in front of it, little m, and big G. So in this regard, we can look at this force vector field. It is actually the gradient vector field of some scalar function. And we can write down what the scalar function is, and we'll do that in just a second. Those kinds of vector fields that come up as gradients of scalar functions are going to be important for us. And those are known as conservative vector fields. So a vector field, capital F, and I should be consistent with my usage of the arrow. There should be arrows on top of these because I'm thinking of these as vectors. So a vector field, capital F, is called conservative if it is the gradient of some scalar function. And that scalar function F is what we call the potential function for the vector field. And so then the question could be raised that the gravitational vector field that we looked at above, that we constructed above, is it a conservative vector field? And the answer, of course, is yes. And why is that? Well, we need to find a potential function for it. So let's figure out what is our little f, our scalar function. Well, following the last example, if we just take the scalar multiple of the reciprocal of the distance the point is from the origin, or the magnitude of its position vector, if you want to think of it that way. If we take little f to be this scalar function, then the gradient of little f is equal to m, big G, times the gradient of 1 over the square root of x squared plus y squared plus z squared. So in other words, I just pulled off the constants. I pulled the constants out front, just so we could use our previous result of, we know what the gradient of this is. The gradient of that 1 over the square root of x squared plus y squared plus z squared is equal to negative x over the magnitude cubed. And that is equal to capital F, the gravitational force vector field. So in other words, this gravitational field is conservative because there is a scalar function for which it is the gradient of. And this is called the potential function.
Jamie?
Yep.
What does it mean exactly for a vector field to be conservative versus not conservative?
So conservative right now is just a term that we use to say that a vector field can be written as the gradient of a scalar. So in other words, in some sense, what we're saying is this vector field is conservative if we can write it as the derivative of another scalar field. And derivative, I'm going to put in quotes here because I'm really meaning the gradient. So it's the vector of partials. What conservative means is in its relationship to conservation properties in physics. So conservation of energy, conservation of mass, these kinds of conservation laws in physics, they turn out to be related to these kinds of conservative vector fields. So that's the deeper meaning of the word conservative. Is there some sort of conservation happening in the background? Now, what is that conservation? Well, right now, these are just, for us, a vector field is just something that takes a vector in and spits a vector out. So we're not assigning it to be, always a gravitational field, or always a magnetic field, or always a vector field of velocities. So we're removing any context from it. So there's, in some sense, we're not talking about conservation laws from physics here, but it turns out that that's the reason this name is coming up, is because it's related to conservation laws in physics. And we'll see, so in some sense, conservation laws tells us there's things that are invariant. so things that don't change. Right? Like, so the energy of a system is not changing. We'll see that there is this relationship to something that doesn't change very quickly in a more general sense. But that involves us getting into integration and looking at integrals over different paths and looking and noticing that there's an invariance of path. I can choose two different paths with the same endpoints, and my integrals will be the same regardless of which path I chose. So that's some sort of deeper connection with conservation and invariance. But does that make sense? So right now it's just a term.
Yeah.
Okay, with deeper connections to physics that we will see. And this is sort of the first connection we see to physics, is that gravitational force fields are conservative force fields. And so there's something to do with conservation laws from physics if you've seen this kinds of thing in physics before.
Thank you.
You're welcome. Oh, and that's the end of this section. Sorry. I'm scrolling down for more, but nope, that's the end of section 16.1. So we're going to move on now to section 16.2. And section 16.2 is now getting into the calculus of these vector fields. So here's our motivating problem. Our motivating problem is we've got a force field that's shown there with all the arrows. Get rid of that. There we go. We've got a force field shown with all the arrows. And then we've got a path. And we imagine a particle moving along a path. So this is, in this case, this is an arch of a cycloid. And so we're imagining a particle moving along the arch of the cycloid. And we've got this force field that the particle is moving through. And we'd like to know what is the work done by this force field on this particle that moves along this path. So it's all right if we don't know how to do this, because that's what I'm using it as a motivating problem for. So let's just think about how we would apply our basic ideas from physics. So I'm just going to pick a point along the path, and let's just say, okay, there's our particle. And what our particle is going to do, and I'm going to zoom in a little bit just so we can get this thing a little bit bigger. So we're imagining our particle is moving just a little bit. So I'm going to draw a little bit of a line. So our particle is moving. What is the work done by a force in moving a particle? Well, the work done by any force in moving an object is just the force times the distance that the object is moved. But it's the force in the direction of motion. So the force that is in the direction that the particle is moving times the distance it moved. So right now I have a force that, I'll sort of make this arrow a bit bigger. So there's my force vector. In this case, I will use capital F to denote my force vector there. Now that's not entirely in the direction that the particle is moving in. There's the direction the particle is moving in looks like this. And so that direction that it's moving in is given by, r prime. So if r is the parametrized curve that's giving this or the parametrization of this curve, this arch of the cycloid, then r prime is going to be the direction that the particle is moving in at that point. And the distance it's traveled, let's say, we can say it's traveled a little distance, I don't know, let's say ds. So if my particle has moved a little distance, so ds, s usually represents the arc length. So that's why I'm using ds. So I'm a little change in the arc length, or a little change along the curve. I want to know what is the force in that direction. And then once I know the force in that direction, I multiply by the distance traveled, and that tells me the work that's done. So what I'm going to need to know is this angle. I actually don't need to know the angle, but I'm going to use this angle to get a formula. So now if I think about what is the force in the direction of motion, the force in the direction of motion is just going to be the magnitude of F times cosine of the angle theta, because that's going to give me the projection onto the tangent vector or onto r prime. So what I've got here is that work, or the little bit of work, I'll call it dw, the little bit of work that's done in just moving it this little bit along the curve is equal to, so the tiny bit of work that's done is equal to the force in the direction of motion. So that's the magnitude of F times cos theta. So that's the force applied in the direction of motion times the distance it's moved. So I'm going to zoom out now and rewrite this formula just on the side here. So what we have is that work is equal to force times distance. And the work done by the force field on a particle moving along the curve is given by, well, there's the little bit, if I move just a little bit along the curve, then it's the force applied times cosine of the angle. So that's the force in the direction of motion times how much I've moved. And now we'll unpack this a little bit more. This is the force applied times cosine of the angle. And what is ds? Well, ds is the arc length differential, the little change along the arc length. And what that is equal to is that is equal to r prime of t in magnitude times dt. So that's what the arc length differential is. In other words, we're just using the result here that, maybe I'll write it over here. Recall ds dt is equal to the magnitude of r prime of t. That's what I'm using. That the derivative of the arc length with respect to t is the magnitude of r prime, or in other words, this is really just saying, in some sense, the speed is equal to the speed, because the speed is ds dt, and another way to write speed is the magnitude of the velocity vector, and the velocity vector is r prime. So, so is that a dot product? So that's a good question. I wrote a dot here. It's not a dot product because neither of these things are vectors. So neither of these are vectors. So this is just multiplication. A dot product will come out. So that dot there is not a dot product, but if you're seeing the future, then yes, this is related to a dot product. And how is it related to the dot product? Now we can go ahead and say, well, let's rearrange this a little bit. This is the magnitude of F times the magnitude of r prime of t times cosine of the angle between them times dt. And this is a dot product, right? This is the dot product of F and r prime, because another way to compute the dot product was to take the magnitude of the two vectors and multiply by the cosine of the angle between them. So this is F dot r prime of t. So make that dot really big. That's a dot product now times dt. And so that's the way to compute the work of this force field on a particle as it moves just a little bit along the curve. And so now what we want to do is work out what is the total work. Well, the total work, let's call it W, would be the integral over all of these little bits of work that are done as you move along the curve. So W is equal to the integral of dW, and we just worked out what dW is. So this is the integral of F dot r prime of t dt. And so this tells us then that work the work done by the force field, on a particle that's moving along this arch of the cycloid is given by the integral of the force field dot the tangent vector integrated with respect to the parameter t. And so we've got our force field F, whatever that is, it's given up top now. We've got our parametrized curve R, that's given there. And so what we end up getting is that we can work it out by just doing this dot product. So this would be the integral from 0 to 2 pi of F at R of t. So that's what it means. We got to plug R of t into our force field. We're going to dot it with the derivative, which is 1 minus cos t. 1, derivative of 1 is 0. Derivative of negative cos is sine t, and then dt. So we'll end up plugging in R of t into our force field, taking the dot product, and then just gives us a integral in one variable. So this is a 1d integral. In other words, an integral back from calculus 2. All right, so we'll get some practice with doing these integrals right after we take this motivating example and make it a little bit more formal. So our motivating example had to do with work, but this is not only the application that we have. So what is it, the kind of integral that we've just developed here? These are what are called line integrals, or probably a better term would be curve integrals, because we're integrating over a curve. And these are just one-dimensional integrals. So double and triple integrals are based on integrating a function over an area or volume. But a line integral, which is what we just constructed above, or in other words, a curve integral, because it's called line integral, but we're never integrating generally over just a straight line. So a line in this case is just meaning a one-dimensional curve, or a curve, to be specific. So a line integral is based on integrating along a space curve. There are two types of integrals, and they are, one is we integrate a scalar function with respect to arc length, and the other is we integrate a vector field with respect to a space curve. And that's the second one is what we just set up above. We had a vector field, we had a space curve, and we are integrating the vector field along the space curve. So let's look at the first type of line integral. This is the line integral of a scalar field. And in particular, we're going to look at 2 dimensions. And so we're integrating with respect to arc length. The integral is set up there. So we've got a space curve, which is parameterized by x of t and y of t. And the integral of little f, so the scalar function, along the space curve c is denoted by just a single integral sign with a c as the subscript on the integral sign, f of x, y, and then ds with respect to arc length. What is arc length? Arc length is the magnitude of r prime. So it's the tangent vector, and then you take the magnitude of it. So r prime. In other words, what I'm doing here is I'm just saying that I'm using this ds is the magnitude of r prime of t dt. And so this is what this whole thing is. So the part on the left, the integral of f ds, that's what we're integrating with respect to arc length. But the way we do it is we convert to the parameter for the curve. In this case, it's the parameter t. So we convert to r prime of t and dt. Now, what does this represent? Okay, so it's all well and good to have an integral, but we want to know what this represents. So the idea with this is the following. If we look at that picture on the lower right-hand side, there is a curve C in the xy plane. There is this function capital F, which it's not drawn, the surface isn't fully drawn. All that's drawn is the corresponding points that live above the curve. So if I have a point down here, xy, then the point directly above it is x, y, and then the scalar f of xy, which gives us our z value. So what we're doing is we're just taking all the points on that curve in the plane and working out their third component for those points, that's f of xy, or the z value, and looking at that curve now sitting in space. And there's going to be now this sort of curtain that's formed between the two. And what this integral represents is the area of this curtain. So this integral here represents the area of, I'll call it a curtain, like I'm thinking of these things that hang in front of windows. Right? You've got a curtain rod up top and this sort of sheets hanging down. That's what this integral is representing, at least in the context when this function f is positive. If the function is negative, then of course there's sign issues where things start to cancel out. But that's what this integral is representing. And the way arc length comes into this is if I think about computing the area of this curtain, I'll zoom in a little bit. We've sort of got these guidelines already drawn. What I would do is I would chop up the curtain into a bunch of little bits. And so here's one bit of my curtain. And then I'd compute the area of this little bit. And so I'd look at, okay, what is the area of this little bit? Well, the area of this little bit is the height of this bit, which would be like f of x, I, y, I, let's call them stars. Those would be our sort of sample point in that interval, xi star, yi star. And so this is my height of that sample point. I'm going to approximate it by rectangles. And then I have to multiply by the width. But the width is just the length along the arc. So it's a ds. And so then I add up all of those things. In other words, I integrate over all of these FDSs. And so that's where that integral is coming from. The integral of f of xy ds, and then we just replace ds with what its expression is in terms of t. So this is the line integral of a scalar function. Now I've expressed it in terms of areas, but it doesn't have to be. We'll see examples where these things are related to. If I've got a curve and I know what its density is, so I imagine the C is like some rod that's bent in this shape, and I know what its density is at every xy value along the length of the rod, then integrating the density with respect to the arc length is going to give its mass, for example. So there's many ways to interpret these things depending on the physical context. But in terms of just absence of context, we're going to think of this as the area of this curtain. So let's go ahead and do an example. So we're going to evaluate this integral, so the integral of the scalar function x with respect to arc length, where c is this arc of the parabola followed by a line segment. So let's get our sketch for c. So it's the arc of the parabola from 1, 1 to 3, 9. So I'm imagining a parabola coming out, and then at 1, 1 is where it starts, goes up to 3, 9. So there's 1, 1. There's 3 and 9. And so that's our first segment. Let's call that C1. And that's on y equals x squared. And then what we have is a line segment from 3, 9 to 4, 7. So it goes one more unit along, but it drops down to 4, 7. And let's call that curve C2. And what I'd like to do is I'd like to integrate x along these two curves. Now, the way we can do this integral is we can just split it up into two separate integrals, the integral along C1, the integral along C2. So let's go ahead and do that. To find the integral along C1, we're going to have to find a parameterization of the C1 curve, first of all. So what is our parameterization of the C1 curve? Well, x can be given by our parameter t, and therefore y is t squared. In other words, if we wanted to write it as, a parameterized curve r sub 1 of t, that would be given by t squared. And t is going to range between two values. So I've got to go from the 0.11 to the 0.39. So t is going to go from 1 to 3. So there's my parameterization. So I've written in two different ways, one involving r1 of t, but the other one just involving x as a function of t and y as a function of t. So however you want to do it, you can write it in either form. And now we want to write the integral. So we want to integrate over the C1 curve of x with respect to arc length. So that is, we want to integrate over the C1 curve, which means we are integrating from 1 to 3. We're going to put everything in terms of t now. So x becomes t, ds becomes r prime of t, magnitude. So that is going to be dx dt, which is 1 squared, plus dy dt, which is 2t squared, and that's dt. So that's the integral we want to evaluate. Now we're back into the realm of calculus 2, where we've now got an integral of a single variable. So we'll just continue on a little bit to clean it up. That becomes t integral 1 plus 4t squared dt. And now we're, calc 2 integral. So I'll leave the details there. I would just want to focus our attention on what is the new stuff for us. And that gets us to a value of like 1/12, 37 to the 3/2 minus 5 to the 3/2. Okay, so the new part was setting up the integral. And it's always setting up the integral. That's the challenge, taking the context and setting up the integral. We still have the second one to do. That is C2. I want to integrate over that line now. And in this case, we're not given anything about the line other than just the starting point and the end point. So how do we get our parameterization for the line? I'll write that as r2 of t. So the way to get a parameterization of a line is we can do a couple of different things. One, we could start at the point we want to start at, which would be 3, 9. And then we add to that t times the vector that goes from the starting point to the ending point. And so that would be 1 minus 2. In other words, what's appearing here is the terminal point minus the initial point. So I'm basically saying to get the parameterization, you start at the first point, 3, 9, and you add to that t times the vector that will take you to the second point. And that way, we just have to let t run from 0 to 1. Because once we get t equals 1, now we're at that second point. We're just adding 3, 9 to 1, negative 2, and that gives us our 4, 7. And so there's our parameterization. We can go ahead and set up our integral now. The integral over C2 of x ds is going to be the integral from 0 to 1 of, it's our scalar function with our parameterization plugged into it. So x is 3 plus t. And then ds is the square root of the derivative of x with respect to t. So that's 1 squared plus the derivative of y with respect to t. That's our -2 squared dt. Or in other words, it's the integral from 0 to 1 of 4, so root 5. I'll bring the root 5 out front. Root 5, 3 plus t dt. And that gives us a value of 7 over root 5. Sorry, 7 times root 5 over 2. And so bring these things all together, the integral over c is equal to the integral over c1 plus the integral over c2. And we just worked out those two values. So this gives us a 1/12, 37 to the 3/2 minus 5 to the 3/2 plus a 7 root 5 over 2. So that would be our final value. So again, the idea here was we want to integrate over a curve. So it's almost analogous to integrating along an axis, which we've done all through Calculus 2. All through Calculus 2, we are integrating along the x-axis of some function. Now, instead of integrating along an axis, we are integrating along a curve. So we are using the parameter t as our variable of integration, and we are just putting everything in terms of that parameter t. So our scalar function, we are replacing x and y with their values in terms of t. And the ds, we are replacing it with the values in terms of t, which is the magnitude of r prime of t times dt. So these are examples of line integrals of scalar fields. We can do the same thing in 3 dimensions as well. It just scales up very naturally. So we take our function and we plug everything in terms of t, and then we use the corresponding expression for ds in 3 variables. That's dx dt squared plus dy dt squared plus dz dt squared. Sometimes it's helpful to sort of simplify this, the way we represent this. So we would represent it as the scalar evaluated at the parameterized curve, so f of r of t, and then ds dt just becomes the magnitude of r prime of t dt. So that's just a simplified way to write that full expression. But the bottom line is the same, and we just set up the integral, and it's a 1D integral. So next day we will do this next example, which is just one more dimension, and then we will get into line integrals of vector fields. And that will take us about only half of the lecture on Friday, and then we'll get into 16.3 for the second half of the lecture.